Okay, so just to practice taking the derivative with respect to time, given the equation x plus 4y equals 3. They're giving you the fact that dx dt is equal to 1. They want you to find dy dt when x equals 2. Sometimes they give you extraneous information that we don't even need in the problem. So let's take a look at this particular equation. Let's go ahead and take the derivative of these variables with respect to t. So what's the derivative of x going to be with respect to t? That's going to be a 1 times dx dt. Plus, what's the derivative of 4y going to be? The derivative of 4y is going to be 4 times your dy dt. Equals, again, you're taking the derivative of both sides of the equation, so the derivative of 3 is going to be 0. So that's what we're going to be doing with all these problems. Related rates is you're doing derivatives with respect to time. So now plug in what we know. We know we want to find our dy dt. That's what we're trying to solve for. So if I plug in 1 plus 4 dy dt, that's going to be equal to 0. So what's dy dt going to be equal to? Dy dt will be equal to what? Negative 1/4. And typically, with most of our related rate problems, since we're dealing with applications, you're going to have units. The units will typically be something over time, depending upon what they're asking you to solve for in the end. All right? So then for part B, very similar situation, except now they want you to find dx dt. Notice that x equals 2 in part A and x equals 3 isn't even going to come into play in the problem. That's that extra information I was talking about. So again, to find your dy dt, I want to, using the same equation, dx dt plus 4 times dy dt, which is 4, is equal to 0. So what's dx dt going to be equal to? Dx dt will be equal to, what? 16. Negative 16. Okay? So that's basically the process of related rates. You're going to find a derivative with respect to time. You're going to plug numbers in, and then you're going to solve. The trick is figuring out that first equation that you want to find the derivative for and pulling that information out. So let's take a look at the first example here. We have a stone that's dropped into a still pond that sends out a circular ripple whose radius increases at a constant rate of 2 feet per second. Looking for my highlighter. How rapidly is the area enclosed by the ripple increasing at the end of 12 seconds? So first of all, what geometry formula do you think is applicable to the problem? What's the shape that we're dealing with? We're dealing with the shape of a what? Circle. And we want to know how rapidly the area is. So what is the appropriate geometry formula we're going to apply to this problem? Area of a what? Circle. So what is the area of a circle? Pi r squared. So we're talking about the radius increasing at a rate of 2 feet per second. Is that the length of the radius, or is that the rate of change of the radius? Rate of change. So what are they giving you there? They're giving you the derivative. That's a derivative. So I'm going to label that as my dr dt. The derivative of the radius with respect to time is 2 feet per second. How rapidly is the area enclosed by the ripple increasing? They're not asking me about the actual area, are they? No. So I'm not finding the area. I'm finding the rate of change of the area. So what do they want me to find? They want me to find the derivative, correct? The derivative of the area with respect to time. When they talk about something increasing, decreasing, or changing over the time, they want you to find the derivative of the area, the rate of change of the area. So I'm going to solve for dA dt at the end of 12 seconds. Okay? So any questions on what I'm solving for are the pieces of information that I have found. All right, so first of all, let's go ahead and let's take the derivative of my area formula. Again, I'm doing it with respect to time. So the derivative of the area with respect to time is going to be a dA dt equals What is pi? Pi is just a what? Constant. So then I have to take the derivative of r squared. And what is the derivative of r squared? 2r. So this is going to be 2 pi r times your dr dt. Remember, to solve this, you should only have one unknown. All right? Well, they're giving me by dr dt. That's great. What piece of information do I have to plug in on the right-hand side that I'm missing? I have to plug in a what? R. So that's the question. They want me to find the rate of change of the area at the end of 12 seconds. Well, they're telling you that the radius is increasing constantly at a rate of 2 feet per second. So at the end of 12 seconds, what's that radius going to be? The radius at the end of 12 seconds is going to be what? 24. So now I have all the pieces that I need. I can go ahead and I can answer the question. So dA dt is going to be equal to 2 pi times 24 times my dr dt, which is 2. So 2 times 24 times 2 is going to give me a what? 2 to 48. 48 times 2 is 96 pi. And it's 96 pi feet per second. These could kind of eeny, meeny, miny, mo. I've seen these on calculator FRQs. I've seen them on no calculator FRQs. They are probably more commonly appear on the no calculator FRQs. Yes?
Like, does it matter if your label is right? Like, isn't it feet squared second?
Yeah, it should be feet squared. You're absolutely right. It should be feet squared. Thank you. Yep, you're absolutely right. I should put that there. Thank you for bringing that up. Yep, feet squared. So it's area. Thank you. So any questions on the area? Circle problems are common. All right, so definitely we should hopefully all remember the area of a circle. So let's take a look at example 3. A spherical balloon is inflated so that its volume is increasing at a constant rate of 4 cubic feet per minute. How fast is the diameter of the balloon increasing when the radius is 2 feet? So the question is, what is the appropriate geometry formula we're going to have to remember? We have to remember the volume of a what? Sphere. So volume of the sphere is going to be 4/3 pi r cubed. So let's pick out what they're giving me. They're telling me that the volume is increasing at a constant rate of 4 cubic feet per minute. So that's not the volume, that's the rate of change of the volume, correct? So they're giving me that dV dt is equal to 4 cubic feet per minute. They want to know how fast is the diameter of the balloon increasing. Well, they don't know we don't want to know what the diameter of the balloon is. We want to know what's the rate of change of the diameter. So we want to find the rate of change of the diameter. So I'm going to call that dd dt when the radius is 2. Well, if the radius is equal to 2 feet, the diameter is going to be equal to 4 feet. The trick with these related rate problems, a lot of times you may have to rewrite the appropriate formula that applies to the problem so that it relates to what they want you to solve for. Notice my sphere formula is in terms of the radius, but they want the answer in terms of the diameter. So what I need to do first is I need to change this formula and I need to rewrite it in terms of the diameter. Well, I know my diameter is equal to 2 times the radius. So if I want to rewrite r in terms of the diameter, then I can divide by 2, so the radius is going to be equal to d over 2. Because before I do this derivative, I need to get rid of that r. All right? Because if I take the derivative right now, what's going to happen is I'm going to get a dr dt, which I'm going to be stuck. I'm not going to have enough information to solve it. Now I can rewrite my formula, so the volume is going to be equal to 4/3 times pi times d over 2 to the 3rd power. You want to clean this up, make it as pretty as you can, before you differentiate. So we want to actually multiply, get rid of those exponents. So again, I know that this is going to give me d to the third in the numerator over 8. So I have 4/3 times 1/8 times pi d to the third. I just rearranged the order there. What's 4/3 times 1/8? It's going to be 1/6 or pi over 6 d to the third. Any questions on how I rewrote that volume formula in terms of the diameter? You guys go ahead and finish this for me. Go ahead and plug in, take the derivative and plug in what. Okay, so let's take a look and see what you guys come up with. Once you reduce, I came up with your rate of change of y is going to be negative 15 over 2 feet per second. Is it okay to get a negative number? Yes, because what direction is this ladder going? It's going down. So any questions on that one? Yep.
Would positive still work because it's asking for the speed
Going down?
Yeah.
Yes. Mm-hmm. If it did not say this key phrase right here, the moving down, then you'd want to make sure you include the negative, or you'd want to state that the ladder is moving down the wall. Okay. So like I said, triangles, ladies and gentlemen, it's always Pythagorean theorem, or it's going to be a trig ratio. The trig ratios are pretty obvious because they're going to be giving you some kind of angle. All right? The cones. Sand is pouring from a chute, and it's forming a conical pile whose height is always equal to the diameter. If the height increases at a constant rate of 3 feet per minute, at what rate is the sand pouring from the chute when the pile is 8 feet high? So here's a cone. Don't laugh at me, I'm not an artist. It's a pretty good cone. So, ladies and gentlemen, let's talk about the geometry formula that's going to be applicable to the problem. If I've got sand pouring from a chute and it's forming a pile, what am I talking about, or what's changing over time? Is it the area or is it going to be the volume? Volume. So let's talk about the volume of a cone. 1/3 pi r squared times h. There's your volume of a cone. So now let's look at, with these cone problems, ladies and gentlemen, you never, ever, 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 ever want to have the two different variables in here, because that means when you go to derivative, it's going to be a product rule, which means you'll have a drdt and you're going to have a dhdt, and you're not going to have enough information to solve it. With the cone problems, probably about 99% of the time, you're always going to rewrite in terms of h. They may very rarely have you in terms of the radius. Most of the cone problems, saying most, not all the time, it's going to be changed. You're going to be rewriting the formula in terms of the height. They're always going to give you some kind of relationship between the radius and the height, or in this particular case, they're giving you the relationship between the height and the diameter. So when we go to rewrite this formula, they're telling you that your height is equal to the diameter. This cone formula nowhere in it has a diameter. So we know that we need to rewrite the diameter as 2 times the radius. On occasion, I think I've seen one over all the FRQs that are released where you had to rewrite it in terms of the radius and not the height. Before you decide whether you're going to solve for h or solve for r, let's figure out what else they're giving me in the problem. So they're also telling you that the height is increasing at a constant rate of 3 feet per minute. So what is that in terms of the height? Is that the actual height, or is that the rate of change of the height? Rate of change. So we know that dH dt is equal to 3 feet per minute. At what rate is sand pouring from the chute? So the sand pouring from the chute forming this pile is affecting the rate of change of the volume, isn't it? So we want to find dV dt. When the pile is 8 feet high. So if the pile of sand is 8 feet high, what are they actually giving you here? They're giving you what? The height. So now let me ask you this. Do I want this cone formula to have all R's in it or all H? H. Because they gave me no other information about the radius. All I know is I know dH dt, and I know my, I want to know what the rate of change of the volume is when the height is 8. So what I need to do is I need to rewrite now the formula in terms of the height. So then I know that H over 2 is equal to R. So I have 1/3 pi times H over 2 times H over 2 squared. Clean this formula up as much as you can before you do the derivative. So when I clean this up, I still have pi over 3, and H over 2 squared is going to give me H squared over 4 times H, so that's going to be H to the 3rd over 4. So the volume is going to be pi over 12 times H to the 3rd. So any questions on how I rewrote the volume of that particular cone? All right, you guys go ahead and finish it for me. Go ahead and find your dV dt. 48 pi cubic feet per minute. So let's take a look at the last example. This is another triangle problem, and like I said, the triangle problems are either going to be the Pythagorean theorem, or it's going to be some kind of trig ratio. So let's take a look at example 6. An aircraft is climbing at 30 degrees to the angle to the horizontal. Here's my horizontal, and there's the path of the aircraft. How fast is the aircraft gaining altitude? So altitude is always perpendicular to the ground. So I'll call this my triangle. I'm talking about the height or altitude. So they want me to know how fast is the aircraft gaining altitude if its speed is 400 miles per hour. So the speed is 400 miles per hour. Now, is this your actual length, or is this a rate of change? Rate of change. So what do they want me to find? Not the actual height, but the what? Rate of change of the height. So I need to find dH dt. When ds dt is equal to 400 miles per hour. So this is an example of the triangle problem where it's not going to be Pythagorean theorem. So let's talk about what trig ratio may be applicable to this particular problem. I'm given an angle, and I'm talking about the rate of change of the side opposite to the angle and the rate of change of the hypotenuse. What trig ratio comes to mind? Sine. So if you remember, I know that the sine of 30 degrees is equal to the opposite over the hypotenuse. There's a lovely trig question. Sine of 30 degrees. 1/2. Very good. So I have 1/2 is equal to h over s. So if I want to solve for h, I'm going to multiply both sides by s. So I have 1/2 s is equal to h. Any questions on how I've set that up? Now we're ready to go ahead and take the derivative. So I have 1/2. The derivative of s with respect to time is going to be your ds dt. Derivative of h with respect to time is going to be my dh dt. What are they telling you about ds dt? ds dt is what? 400. So 1/2 times 400 is equal to dh dt. So then I have 200 miles per hour is the rate of change of your altitude. Okay. Like I said, those are the triangle problems. The triangle problems are either going to be trig ratios or Pythagorean theorem. Okay, guys, go ahead and take out your laptops.